Okay, we're going to take a dive into chapter 8 today, and we are going to take a break from math, which is good on multiple reasons. Number one, it's easier to show you some of these things when I'm not dealing with equations and numbers and trying to set these up using dimensional analysis. In this chapter, we're going to start getting prepared for understanding chemical reactions, what's involved, what roles they play, and then we'll come back to the math in the next chapter. So, in this first part of chapter 8, we're going to be taking a look at chemical reactions. We're going to describe the reactions. What I mean by that is we're going to recognize what roles things play based on where they are listed and certain aspects of a chemical reaction that tell us certain things about how the reaction occurred. In the second part, we're going to interpret these chemical reactions. What I mean by that is we've gotten used to reading letters and numbers for formulas, but since we've covered naming chemical compounds in chapters 5 and 6, we're going to start to apply that skill. So actually, when we go through these equations, we're going to sound like scientists. So don't forget to go to the bottom of that page and download the Chapter 8 packet. And there's also going to be a 6-page packet with some tables in there that will be useful for future reference when we start to apply some of these skills in a more advanced method later on down the line. So let's get right into it. A lot of this is going to be review with just a little bit of new material. Okay. Now, when we're talking about chemical reactions, the first thing to note here is that we're going to be looking for a chemical change. So we're looking for evidence of that. So one of the things that I'm going to have you guys review is how do you recognize whether or not a chemical reaction is actually occurring versus this is just a physical change. So you're looking for evidence of that new substance forming. Now, a couple things that can tip you off to this is that the properties are going to be different. And when we actually write these chemical formulas, they're going to be in new arrangements. So the atoms are not going to be in the same chemical compounds that they were to begin with. We talked about some of this at a previous time. One of the things you look for is a change in the amount of energy. Things can either get hotter or colder. They can release or absorb energy. Now, that energy can take a variety of different forms. In the exothermic, they're giving off energy. You can see there are two examples here. One of those is exothermic in the manner that it gives off light, and the fire not only gives off light, but also gives off heat. In the reaction to the right, I actually demonstrated that for you. I took some ammonium chloride, and what I did was I mixed that with water and it started to get very cold. In this example, you can see that it will actually freeze itself to a wet block of wood because it'll get cold enough. Good example of this would be those disposable ice packs that athletes use if they get injured during an event or something like that. There's a little packet of water inside of there. And when you mix it with water, it'll actually start to get colder through time. Another example we took a look at are changes in color. The one on the left, what you're seeing there is an acid-base reaction with an indicator called phenolphthalein. The beaker on the left is clear, but it contains a base solution of sodium hydroxide. When I insert phenolphthalein, an indicator, it actually reacts with that to form a pink color. In the reaction on the right, what you're seeing there is a copper wire being lowered into a solution of nitric acid. And that nitric acid reacts with the copper to form a solution of copper nitrate, which has a deep blue color. Those are just a couple examples of color change. Another example would be if a gas is given off. Sometimes you can see it in the case off to the far left. That's another reaction. That's a more violent reaction with copper and nitric acid, but it's a much more concentrated solution. You're seeing a nitrous oxide gas being produced, and that forms that reddish orange color gas that's being emitted. In other cases, you can see bubbles forming, as in the case with baking soda and vinegar, or you might not be able to physically see it, but you'll be able to detect it because there will be a change in the odor. It doesn't have to be necessarily noxious, or it could be just the reverse of that. It once had an odor and it doesn't. Now, remember, odor itself is a physical property, but the change in that is an indication of a chemical change. And then the last one would be the formation of an insoluble salt. This is going to become important later on to determine whether or not a reaction actually happens when we get into something called a double replacement reaction. But when you mix two clear solutions here, on the far left, you're going to see a solution here of lead nitrate mixed with sodium chromate. Now, we don't do this one actually in the lab because lead is toxic and so chromium. But what you're seeing form here is a yellow salt called lead 2 chromate. And that will not dissolve in water, so it forms this cloudy yellow mixture that will eventually settle to the bottom. So these are just different examples of mixtures that form cloudy precipitates. So when you look for evidence of a chemical change, ask yourself, in a certain circumstance, could you identify one of these four forms of evidence? Now, the other thing that I want you to be able to do is tell me what the parts of a chemical reaction are. These are some of the key aspects of a chemical reaction. The reactants are things that are generally found on the left side of the equation, while the products are generally what's found on the right side of the equation. And the yield is the arrow that tells the direction of the chemical reaction. What you're going to find out is sometimes the yield can point in both directions. That means that the reaction is reversible. And sometimes we'll have little things written above that arrow. Sometimes a catalyst and sometimes energy. There are numbers written in front of chemical formulas at times. Those are big numbers. Those are called coefficients. And we've been working with subscripts. Those are the numbers that are written below the chemical element. And those are used to make sure that the number of atoms in a chemical compound are correct. Phase will become important later on as well. Generally speaking, your phases are going to either be solid, liquid, gas, or aqueous, meaning dissolved in water. Those are written after the chemical formula in a set of parentheses. And then there are a variety of different ways we can insert energy into an equation as well. So this is an example of one of those chemical equations. Now, you note that there are coefficients. That's what the 2's written in front are. Subscripts, phases, and then a yield arrow right here. And this tells me that the reaction is going to start out with the reactants and end with products. Now, this is a chemical equation, meaning it's written as symbols and subscripts. But that's not how you're going to read it back to me. I read this as 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide to produce 2 moles of water and 1 mole of sodium sulfate. Note that this is not hydrogen sulfate because of the AQ. This is a hydrogen compound, meaning it is an acid. It gets a different name. So basically, all you're doing is going through and naming this compound and this compound, and note that these are going to react to form this compound and this compound. So you're simply going to be giving the names. So take a look at page 6, number 1. Real simple example here. When I read this out, when I ask you to interpret, for the time being, I don't care if you tell me the number of moles involved. For the time being, just tell me what the compounds are, which ones react, and which ones are formed. So in this case, you've got H2. Now remember, that's hydrogen in its natural state. So the simple answer there is hydrogen plus oxygen react to form. And you know what this is? That's water. That's all I'm asking you to do for the time being. Now it gets a little more challenging when you go in the other direction. For the second example, I'm going to take one from page 4. On page 4, number 2, you take a look at aluminum bromide plus chlorine yield aluminum chloride plus bromine. INE or GEN elements are going to be diatomic in their natural states. You see how those are Cl2 and Br2. Now, aluminum bromide, aluminum is in column 13, that gets a +3. Bromide is in column 17, that gets a -1. So when I cross those, I get AlBr3, and the same thing over here for aluminum chloride, AlCl3. So for the time being, this is my equation. Now some of you are looking at that and saying, but wait a minute, how did it go from being Br3 to being Br2? That's actually one of the wrong questions to ask. We're going to deal with making sure that the numbers are equal later on. That's a different skill called balancing. So don't worry about that right now. Take the formulas and write the correct formulas based on the names. That's all I'm asking you to do to begin with. So when we do some of these practice questions, okay, it might tell you on pages 4, 5, and 6 to balance. Don't worry about that. We will come back and balance those later on. That's actually a separate process. So don't worry about doing that right now. So now for your practice set. Okay, in the Chapter 8 packet, I want you to do the first 6 pages. So if you take a look at the packet, pages 1, 2, and 3 are going to use a little bit of information from the textbook. I hope you guys brought those home with you. It might be useful to go through and see what the textbook's perspective is on some of these things, and it will explain to you a few other aspects that were not covered in this presentation. And then for pages 4, 5, and 6, you're simply going to be taking names and writing formulas or formulas